This week we were required to drop two objects, one that drops rapidly and one that drops slowly from some height, and observe the motion of the two falling objects. I chose to use a coffee filter for my slow object and a crumpled paper ball for my fast object. Our first prediction model solely looks at the force of gravity on the objects. The graphs for both the ball and the filter show a large amount of discrepancy in distance traveled, so we can conclude that there is an unaccounted for force at work. Since the distance traveled in the models is greater than what was analyzed in Tracker, we can surmise that this unknown force works in the opposite direction of gravity. Our second prediction model contains gravity and a second force, viscous drag. One can immediately see that the addition of the second force aligns our prediction model to fit much more closely than the previous. For the coffee filter, there was discrepancy in the beginning that could be attributed to the nature of the filter to swing slowly side to side as it drops. As for the paper ball, there is still discrepancy in the graphs. This could be due to the fact that the paper ball is a poor model for drag due to its shape. An object with greater surface area, like the coffee filter, works better. What does it mean? We analyze the slope of the position versus time graph to see what is happening with the velocity. With just gravity, the coffee filter slowly drops in the beginning and speeds up as it continues to fall. Towards the end, we see that the filter begins to fall at a constant speed. When we model gravity with drag, the filter's speed is constant from beginning to end. This type of constant speed is a type of velocity called terminal velocity. Net forces acting on the filter equal 0, and the speed is constant. Comparing these models gives us insight into drag force's relationship to gravity. Drag force is directly proportional to gravity and must increase at the same rate as gravity for the net forces to cancel out. What would happen if we threw the objects instead of dropping them from rest? In the case in which only gravity is at work, the objects will have an initial speed and will accelerate downward in the beginning as gravity pulls. Then it will fall at a constant rate once time has allowed gravity's full effect to take place. The object will reach terminal velocity as long as no other forces act. If we model with gravity and drag, we will see that the object has its initial speed from the throw in the beginning, but instead of continuing to increase in speed, the object will slow down due to the effects of drag force increasing as gravity increases. The object will slow down until it reaches terminal velocity. At this point, drag force will equal the gravitational pull, and the object's speed will be constant until it hits the ground.